Okay, so I just wanted to say a few words about the restrictions that we make to trig functions to make them invertible, and why we use those restrictions and what that means in regards to integration by method of trig substitution. Because, even though I'm not holding you responsible for it, I think it's important to sort of understand what's going on here. And of course, you do need to know the inverse trig functions and the standard restrictions of them. Okay, so let's come back to what three trig functions we use in integration by trigonometric substitution. Well, of course, there's the function sine theta. It's obvious, right? And if we were to think of sine theta as invertible, we'd have to restrict the domain. So let's do a quick graph of sine theta here and remind you of what we restrict the domain to make it invertible. If you recall, negative pi over 2, pi over 2, and let's do a pi here. And of course it goes down to negative 1 and up to 1. And if I graph the sine, it looks something like that. And of course it repeats over and over again, forward and backwards. But as you note, so let's draw the repeating here. Of course it's not invertible, but how do we make it invertible? Well, we restrict the domain, and generally we restrict it to the simplest one that makes it one-to-one, right? So the domain restriction we use is, can I use this thing? Is, look at that, isn't that cute? Is the one that makes it one-to-one. If I keep it there, that's one-to-one. Let's undo that and make it skinnier. There we go. If I restrict it there, it's going to be one-to-one. And what is that domain restriction then? That's going to be negative pi over 2 less than or equal to theta less than or equal to pi over 2. In other words, if theta is in that range, everything that can come out of the sine function will come out of it in that range, right? Negative 1-to-1, everything will be covered. Everything that we get in the sine function here from negative 1-to-1 will be covered if I restrict the domain to that. But this has a further advantage. Not only is it 1-to-1 and does it cover everything, the further advantage is, let's draw the circle. Make sure we understand the circle definition. Let's undo that one. Oops. And let's try that again. See if I could draw a vertical line there. Okay, vertical line enough. And circle, I could probably find something that will draw a circle for me, but I'm going to stick that here. Okay, imagine that's a circle. So with that restriction, from negative pi over 2 to pi over 2, what we're doing is going around this way, right? Negative pi over 2 is there. Up to pi over 2 is here. And remember, cosine is the x-coordinate. So if I have a certain angle here, call it theta. Theta, cosine of theta is the x-coordinate of that, of where that ray hits the unit circle. That's a circle of radius 1. So cosine is going to be the x-coordinate of that. If I have any ray on this portion of it, of course the x-coordinate is going to be positive. In other words, we know that cosine of theta is bigger than or equal to 0 if we have this restriction here. So more to the point, and I've mentioned this a few times, but let's just point out, how does this work with regards to trig substitution? Well, when we go through and we look at 1 minus sine squared theta, of course that's cosine squared theta. And generally speaking, as I've mentioned over and over again, this is actually absolute value of cosine theta. But if we have the restriction I gave you, cosine theta is bigger than or equal to 0, and so that you can just ignore the absolute value. Furthermore, if I'm doing an integration, by trig substitution problem, and I end up with, having to solve for theta, so I've got theta plus whatever else is going on here. Well, how would I do that? I would solve for theta. Basically, I've got x equals sine theta. Theta should be the arc sine of x, right? Or arc sine of whatever it is that is equal to sine theta. Now, I can only do this if theta's in the interval that arc sine is restricted to, if theta's in this interval. So there's two reasons for this restriction. One is that is how we're defining arc sine. It's the inverse of sine restricted to that. And two, it's convenient because the cosine of that angle, any angle with that restriction is going to be positive, and so we can take the square root. Okay, so now let's look at the other two ones, just to make certain we're in the right. We're doing this. So let's go back to color, and let's get some more room here. Extend page. Okay, so what's the other one? Let's do x equal tangent theta. Well, what's the standard restriction of tangent theta? Again, the standard restriction of tangent theta is negative pi over 2, strictly less than theta, less than pi over 2. And if you look at the graph of that, that makes sense, right? Because the graph of tangents from negative pi over 2 to pi over 2. And of course, it repeats over and over again. It's got period pi, right? We could go to 3 pi over 2 and so on. The graph has vertical tangent asymptotes at negative pi over 2 and at pi over 2. And it repeats like that. But if I restrict it to this area, if I restrict it to this piece right here, oops, undo. If I restrict it to this piece right here, it's going to be 1-to-1 on that piece, and everything that can come out of the tan function will come out. All real numbers will be gotten by that way. So this is a perfectly reasonable restriction, but what's more to the point is that in that restriction, of course, when trig substitution, why do you use it? You use it because 1 plus tangent squared equals secant squared, right? So we end up with things that look like 1 plus tangent squared theta, which is secant squared theta. And if that's under the square root, well, usually that would be the absolute value of secant theta. But in that restriction, again, that restriction is here, right? That restriction's from negative pi over 2 to pi over 2, right there. And if theta's in that restriction, well, secant is 1 over cosine. So as we pointed out, cosine's positive in that restriction, therefore secant is positive, or at least bigger than, well, in this case, strictly positive. And so the square root of secant is simply, the absolute value of secant is simply secant if we have that particular restriction. And furthermore, again, if you have theta in your answer, you can solve for theta by simply applying the arctangent, which you can't do if we had another restriction to it. And then finally, let's just look at secant theta. Now, if you recall, secant theta had a really weird restriction, x equals secant theta. Let's look at the graph of secant theta. It had negative pi over 2. It had asymptotes at pi over 2 and negative pi over 2 and 3 pi over 2 and so on down the road, right? And it looks like u's and upside down u's in between, right? It's got those asymptotes there, and it looks like u's and upside down u's. So the range is from 1 to infinity, and from -1 down here to negative infinity, or negative infinity up to -1. So the restriction is going to be something that gets everything in the range, but it makes it 1 to 1. So, of course, the simplest thing is going to be from 0 out to pi over 2, right? So let's say the restriction is 0 less than or equal to theta less than pi over 2, because it can't equal pi over 2. And the question is, which half of this other bump do we get? Do we get this left half, or do we get the right half? And as we saw in class, when we did the inverse trig functions, we actually took the right half here. So we actually had that, or the right half is pi less than or equal to theta less than 3 pi over 2, right? That was the restriction for secant that we took to make it invertible. This is the arcsecant is the inverse of the secant function restricted to those two intervals, from 0 to pi over 2 and from pi to 3 pi over 2. Those aren't the only restrictions we could have taken, but they're restrictions that work. It's 1 to 1 on those intervals. But the reason we chose this restriction is because in that restriction, let's just look at the circle definition again. Again, let's think about how this comes up in trig substitution. In trig substitution, we're going to be simplifying something of the form secant squared theta minus 1, right? Which, of course, is tangent squared theta. So if we're taking the square root of that, as mentioned above, that would usually be the absolute value of tan theta. But let's look on the circle. The restriction that we're working with is theta from 0 to pi over 2, right? That goes all the way up to a right angle. And from pi to 3 pi over 2. And if my angles in there, notice that in this first quadrant, both sine and cosine are positive. So tangent's going to be positive, right? Sine over cosine. In this third quadrant, both sine and cosine are negative. So tangent's going to be what? Yeah, positive. So that means with that restriction, tangent's always non-negative. So the absolute value of tangent is just tangent. And again, if we have to solve for theta in a trig substitution, if we have this restriction, which is the definition, the restriction we need for the secant function, we can always just solve for secant by using theta by using the arcsecant function. And that's it.